Let's work through an example of using cylindrical coordinates to compute a triple integral. So the problem is to compute the volume of a region E in 3 space, and the region is 1/4 of a ball of radius 2. So this is a picture of our region E, and in rectangular coordinates it's given by x squared plus y squared plus z squared is less than or equal to 4, and the coordinates x and z are at least 0. Okay, so this is our region E, and we can see that the boundary curve for this is when x squared plus y squared plus z squared equals 4, and that's this interesting surface here. And then we have x equals 0 and z equals 0, these flat boundary surfaces on the side and below the surface. Okay, so that's our surface E, and if we solve for the z coordinate, of course we know that z is at least 0, and using this equation it's pretty clear that z is less than or equal to 4 minus and then x squared plus y squared, but that's just equal to r squared using the polar coordinate r. Alright, so we can solve for the z bounds, so we'll integrate with respect to z first. So if we compute some triple integral over E, we're saying we're going to integrate with respect to z first. Now the other thing we need to define, we'll talk more about the bounds of E, but the question is, what function do we want to integrate to compute the volume? And the answer is we want to integrate the constant function 1. So just like when we integrate 1 dA, we get the area of a region in the xy plane. If we integrate 1 dV, then we get the volume of the thing that we integrate over. Alright, so now the question is, what are our bounds for r and theta, the other two cylindrical coordinates, which are really just the polar coordinates in the plane. Now we know that we're always going to have to throw this r out in front because that's how polar coordinates and so cylindrical coordinates work. And so what we get when we set z equal to 0 in this equation is we get x squared plus y squared is less than or equal to 4, which is a disk of radius from 0 to 2 in the xy plane, but we also have that x is at least 0. Okay, so we know, look at what this is. It's simply the half of the disk that sits below E, and so it looks something like this. Not the best picture, but it'll do. And so we have this region right here. Now in polar coordinates this is pretty straightforward to describe. It's actually a polar rectangle. So it's r is bounded from 0 to 2, and our theta bounds are from minus pi over 2 to positive pi over 2. Okay, so now we have our bounds for z, r, and theta, so we can write our integral. So we're integrating 1 times r. So our z bounds are from 0 to the square root of 4 minus r squared, and then our r bounds are from 0 to 2, and our theta bounds are from minus pi over 2 to positive pi over 2. Alright, so at this point we're set up, and now we're just going to do this triple integral. So the first thing we're going to integrate is with respect to z, and this is a constant function with respect to z. So in the end we just get minus pi over 2 to pi over 2, 0 to 2, and we get r times z evaluated from 0 to root 4 minus r squared. We still have a couple iterations to go, dr and d theta, and so we get minus pi over 2 to pi over 2, 0 to 2, and this is just going to be r times the square root of 4 minus r squared dr d theta, because the other bound is 0. Okay, and this antiderivative isn't too hard to compute because we can use a u substitution for 4 minus r squared, and we have this r factor in the integrand which allows us to get away with that. because now our bounds are constant and this is just an integral in terms of r, the antiderivative with respect to theta can be separated out, and since it's a constant function of theta, this is just going to contribute a pi over 2 minus a negative pi over 2, which is simply pi. So the antiderivative of this function is going to be 4 minus r squared to the 3 halves, and we just have to account for some constant. So when we take the derivative of this, we get the 3 halves down front, and then when we take the derivative of the inside, we get a minus 2r. So in the end, we're off by a minus 1/3. All right, and then we have to evaluate this from 0 to 2. Now, if I'm moving a little bit fast for some of you, that's fine. You can pause the video and work it through on your own and check that I get to the right point. And you can go back and review your work with integration and get to the point where you can go through these fairly quickly. Okay, so we get minus pi times, and then when we plug in r equals 2, we get 4 minus 2 squared, which is 0 to the 3 halves. So 0 to the 3 halves. And then minus, when we plug in r equals 0, we get 4 minus 0 is 4 to the 3 halves. So 4 to the 3 halves. And then there's that factor 1/3. Okay, so we lose this term, and these minus signs cancel out, and 4 to the 3 halves power is 2 cubed, which is 8. So in the end, this simplifies to 8 pi over 3. So the volume of this three-dimensional region E we've computed using a triple integral to be 8 pi over 3. Now, some of you might have realized right off the bat, well look, this is, since the boundary is a sphere and this is this nice portion of the ball, essentially it's a quarter of a ball of radius 2, we didn't necessarily need to use a triple integral to compute this. Instead of, we could say, so it's 1/4 of a ball of radius 2, so the volume is 1/4 of, and then the formula is 4/3 pi times 2 cubed, which the 4's cancel out, and I'm left with 8 pi over 3. And that calculation was much simpler, but that's relying on this formula, 4 pi r cubed, for the volume of a ball of radius r, and you know that formula had to be derived somewhere. Now, one of the ways to derive it is with a triple integral, and so the work is essentially equivalent to the calculation we just did. It's just more general, or you can possibly use some geometry, you know, that doesn't rely on calculus. But the point here is to both compute this volume and learn how to work with triple integrals, and so that's the method that we use. All right, so the big takeaway is to use the function 1 to integrate dv to get volumes, and to learn how to use cylindrical coordinates and triple integrals, so we can essentially use polar coordinates in the plane and the coordinate z, which in the end gives us the integrating factor r, just like we had with polar coordinates. And this allows us to do a lot of integrals that are well suited for polar coordinates, but in the end our triple integrals in R3.